In this video, we're going to discuss performing uranium enrichment calculations and the more general relative efficiency analysis in InterSpec. The key to relative efficiency analysis is that if you divide a peak area by the nuclide's activity in branching ratio for that energy, you then expect the results to all fall along a smooth curve, at least above the X-ray absorption edge. So for uranium, above 120 keV or so. Of course, the shape of this curve will change with attenuation and detector response function, but it should be a smooth curve. And if you're willing to accept knowing just the ratio of activities of the nuclides in the problem relative to each other, and you assume a functional form, you can fit for this curve and the relative activities at the same time from your data, which you can then get the ratio of activities, or for the case of uranium, you can convert this to the ratio of masses. Some things to keep in mind about this type of analysis is that it does not require knowing the detector efficiency or size. You also don't need to know the distance between the detector and the source. And you don't need to know the source or shielding composition or geometry. But it does require having enough photopeaks to fit the relative efficiency curve. So you want these peaks to span an energy range. Also, all the source nuclides should be co-located and homogeneous, and any shielding around them should all be uniform. And the primary information you get out of this analysis is just the ratio of nuclide activities or masses. So with all of that in mind, let's use InterSpec to calculate a uranium enrichment. So like normal, we'll just drag and drop the spectrum onto the application, and I'll open up the relative efficiency analysis tool. So under the tools menu, it is the isotopics from peaks item. And you can see that opened a new tab on the bottom of the screen. And this tool is more or less empty because we haven't fit any peaks. So let's fit uranium-235 peaks first. And this peak looks like it would probably be better with a step continuum. And it doesn't look like there's any other U-235 peaks at higher energies. So let's fit the uranium-238 peaks. And you can see the tool's starting to fit this relative efficiency curve. Right, so this is an important peak, the 258 keV. We'll come back to that. Now let's fit the higher energies, and these peaks aren't fitting great by default, so we'll just adjust them as we go. Here, I'll use the control key while dragging the mouse to fit a peak. And we don't have to fit all the peaks. We'll just get kind of the prominent ones in the different energy ranges. And you can see the relative efficiency curve is starting to form here. And we can adjust the functional form of this curve. So here we'll make it a fourth order curve. And we'll add a little bit of additional uncertainty to each of the peak areas. You can see we get a nice smooth curve. And we can look at the textual results of this. And we see that it comes up with 4.49% U235. A whole bunch of other information here, but we can see we get the enrichment of about 4.49. You'll notice we didn't use any of the peaks down here below 120 keV, and this is because of the X-ray absorption edge of uranium. If we're going to analyze multiple spectra of the same nuclides, there's a shortcut. We can download the CSV file of the peaks on the Peak Manager tab. And this way, when we load a new spectrum, what we can do is just drag and drop that CSV onto InterSpec, and it will try to fit all those same peaks. And this new spectrum doesn't have all the same peaks as the old one, but that's fine. And now if we go back to the isotopics tool, you can see that everything's pretty much done. There is one peak here that is a small peak in this new spectrum, so we can go ahead and remove that from the analysis since it didn't add much. So now we'll try a little bit more involved of an example. So again, we'll just load our spectrum of interest, and we'll fit the U235 lines here. And in this spectrum, it looks like there are some higher energy U235 lines, which we will happily take as well. Because as you noticed before, U235 tended to be lower in energy, while the 238 lines were higher in energy. And it was the 258 keV of uranium-238 that linked this low energy and high energy range. So we'll take as high energy U235 lines as we can. Again, we'll fit the U238 lines here, and we just gotta grab the prominent ones. We don't need all of them. And now in this spectrum though, you can see that there are some uranium-232 lines as well, which these are great because they span the entire energy range of U235 and 238 of this spectrum. So this will help fit for a consistent curve that spans from low to high energy range. So let's go through and fit the U232 lines. We'll skip the 511 keV because it has some interference there. We'll grab the other lines. Now, an issue with U232 lines is that they overlap background lines. So if we load a background spectrum, you can see that there is some interference from the background, and we're going to want to correct for that. So to do that, we'll load the background spectrum as the foreground for just a moment, and we're going to go through and fit the peaks in the background spectrum that might overlap with peaks that we're using in the foreground spectrum. We don't need to worry about doing a nucleotide ID and associating the correct nucleides with these peaks because InterSpec will just match on energy between the foreground and background peaks. And if we fit extra peaks in the background that we don't use in the foreground, that won't be a problem. So when InterSpec does this background peak correction, it will properly take into account the statistical uncertainties fit in each of the peaks. The other thing we could have done is just do a hard background spectrum subtraction, but then the statistics would be slightly messed up. But the results would still be fine, probably. All right, we'll switch back to the foreground spectrum. And now we'll open the enrichment tool. And you can see there's a background subtract option in the lower left. And if we click that, see the result on the right change just a little bit. And now we're going to try to find a functional form for the curve that's as smooth as possible. And really what we're going here is just, we want the best looking fit we can get. So we'll add a little bit of additional uncertainty to each of the peak areas, and we can try some of the peaks here. So by default, InterSpec recommended not using these peaks, probably because of interferences or something. So we'll pick which peaks we want. We could age the nucleides if we wanted, but just leaving them at 20 years for uranium seems to usually work fine. And really, this is probably the best looking fit. It's not an exact science, but this spectrum turns out to be about 21.5% enriched. So a nice thing you can also do is export an HTML report. So if you click this link, you'll get a HTML file, and in that file is a ton of information about how your answer was derived. You can interact with the spectrum, see your peak fits, mouse over the efficiency points to see what contributed to them. It's nice to keep a record of how you got your answer. Even though this video focused on uranium enrichment, the same methodology and tool in InterSpec should work for any of the other nuclides. So for example, if you want to calculate the activity ratio of fission products after a nuclear release, this should work just fine. For more information, you can see the relative efficiency analysis tutorial on the InterSpec webpage.